All right, everyone. We have a full class today. So we're going to do domestic Recirc first. We're going to pause for questions, and then we'll move into pressure boosters, and then we'll cover questions at the end of that. If we run a little bit over, we will hang on and answer all your questions as long as it takes, and you can stay on. If you need to hop off, we totally understand. Asking questions, I had a few questions about asking questions. So you can either use the chat function or the Q&A function at the bottom of your screen. I'm monitoring both. Remember, we'll do domestic Recirc questions kind of midway through Paul Q, and then we'll go to those. If you have any other questions, please feel free to let me know. And then our email addresses are on the screen right now. So if you need something beyond what's happening in the class, feel free to reach out to us. With that, I'm going to hand it over to our awesome, amazing, illustrious instructor, Paul Campbell. Take it away.
Good morning, everybody. And by the way, if you'd like to share your puppy pictures or your animal pictures, please send us emails. We would love it. That would make our day. So yes, as Sunday said, thank you for joining us this morning. We're going to get rolling. I'm not sure on time, so I'm gonna start cruising. We'll keep an eye on it as we go. All right. So we're going to lead in with domestic Recirc, and then we'll also talk about pressure boosters and hydro tanks and where you put that equipment. Okay. So that's our goal this morning. So bear with me as we get started. So we're going to jump right into domestic Recirc. How it works, how you size a pump, what kind of issues you can have in the field, and some possible solutions for you. I'm going to launch my first poll, if that's okay. It's not about puppies, so I apologize. Let's get going with our first poll. And let me, so we've got that launched. Let me describe what happens in the typical hot water system. And this could be a home, meaning a residence, could be light commercial, could be an apartment or a hotel, could be a multi-story high-rise, doesn't matter. It's all kind of the same as far as what's happening. Every place that we have a load, this might be a shower, might be a hot water faucet, might be a kitchen sink, might be laundry. Each one of these might be a hotel room or an apartment, if you will, any place that's using hot water, we're going to consider a load. And anytime somebody is using hot water, cold water from the city comes in, picks up heat through our water heater, whether that's a storage tank or a tank type, any appliance that's generating hot water, and we send that hot water out through our riser, okay, and it circulates out or gets pushed by city water and ends up at our load, which might be a shower, again, or kitchen sink. You're washing your hands, okay? That's what's happening in a typical hot water system. City water comes in, picks up the heat from our water heater where we're storing it as hot water, and then sends it out to our system where we can use it, okay? But what happens in the middle of the night when everybody goes to sleep, assuming this might be a hotel, okay? The exception might be Vegas, but at 2 in the morning when most people are sleeping, okay, and there's no load going on in the building, everything kind of goes stagnant or no flow at that point. If there's no load in the building, there's no water flowing. So now all this hot water that's sitting in our riser starts to cool down. It gives up its heat to atmosphere or the surrounding space, and it can go cold, okay, or cooler than what we would anticipate when we go to take a shower. So the challenge is, how do we deal with that? Well, we add something we call domestic Recirc. And there's a couple ways of doing this. Heat trace is one, but typically we're going to install some type of pump, okay? And this pump's only job is to circulate our system and to keep this riser warm. Okay, that's its only job. Now, there's a lot of ways to complicate it. Let me end our poll and we'll just share results real quick. Okay, so let me share those. I'll pull those over. In a domestic hot water system, kind of like we've got shown here, the Recirc pump circulates water through the system during which conditions? An open system when people are using hot water, You would think so. That might be true of a pressure booster, but in a typical recirc mode, that's not right. A closed system, when there's no load in the building, that is correct. Okay, so the only time a recirc works or is active is when there's no load in the building. We call that, forgive me, let me stop sharing, get that off my screen. And thank you everybody for participating. But keep in mind, the only time a recirc is active or working in our system is when there's no load in the building, meaning city water isn't flowing. Okay, so our pump comes on, it circulates water again through our water heater out to the system and circulates it as a closed loop, kind of like a closed loop heating system. Okay, as soon as there's a load in the building, meaning somebody's taking a shower, city water comes in. First thing it wants to do is back feed through our recirc system. That's why we have a check valve here to prevent that. But then city water overpowers things and comes through our water heater and continues to send that hot water out to our zone, okay, or our loads. That's all we're doing with a typical hot water recirc. Very simple, but you'd be surprised how easy that gets screwed up in the field. Thank you everybody for taking part of that poll. A couple things to keep in mind. What's a good rule of thumb for getting hot water to a fixture? Well, 10 seconds or less is really a good indication that you've got a good recirc in your system, meaning your riser's staying warm. 30 seconds means we're sending quite a bit of water down the drain before hot water comes behind it. That's dumping a resource down the drain. And if you're 30 seconds or longer, that's really considered unacceptable. We've seen some jobs that are out there 5 minutes, some are 10 minutes before individuals can get hot water to their shower. That's a sign that there's a big system problem. Now, if they're getting hot water to their shower, that would tell you that the water heater is working. Okay, but if it's taking them 10 minutes to get hot water to a shower in the morning, it would tell you there's a problem with the recirc. And think about it, if the recirc's not running or there's an issue there, then all this water that's in the riser that has cooled off overnight has to get flushed down the drain before the hot water can replace it and end up out here at the furthest fixture. So that can lead to quite a delay. That's all that's happening in our domestic recirc. Let's talk about how we size that pump. Again, all we have to do is overcome the heat loss that's occurring in our main riser when there's no load in the building, and that line's basically stagnant. Okay, so there's a heat loss table we can reference. We can also use I want to say industry rules of thumb for delta T, or change in temperature between what we're sending out to the system and what we'd like to see come back on our recirc. Typically that's a 5 to 10 degree delta T. 10 is a lot more acceptable. If you look at a master mixing valve, a lot of those require at least a 7 degree delta in our system. They need a source for cold water, which means we can't come back too hot with our recirc, or this valve starts to hunt and has some operational challenges. If we know our heat loss in BTUs and we know the delta T we'd like to see in our system, we can figure out our flow rate for our recirc that's in question, and that's all we're doing here. So we could look at a heat loss chart. Let's assume we've got a 2-inch riser that has 1/2 inch insulation around it. Well, that 2-inch riser can lose roughly 30 BTUs per foot. So all we have to do is figure out how much piping do we have, and we can figure out what our heat loss is. So quick example, let's assume I've got a building with 500 feet of 2-inch main riser, I want to say it, 2-inch run through our system, okay? And I've got 500 feet of piping total. It loses 30 BTUs per foot. So 30 times 500 gets me to a total BTU loss of roughly 15,000 BTUs. And if I know I want to size my pump for a 10 degree delta T, I can figure out what flow I need. It's just a matter of working this equation a little bit backwards, doing some division and figuring out that my flow needs to be roughly 3 gallons a minute in my recirc system to overcome that 15,000 BTU of loss, then I'm going to see if that line is stagnant or not moving. That's all we're trying to do here. Okay, so now I've got a pump size for 3 gallons a minute. Now pressure drop through a 2-inch line is going to be very minimal at 3 gallons a minute. Okay, it's sized for much larger flow rates. But what I am concerned about is from my furthest load back to the mechanical room or back to my water heater, what line size am I going to use for this, this little section? It's typically not 2-inch. It's usually a half, 3/4, or 1-inch. And we're going to size that based on the flow we need for our Recirc pump. In this case, 3 gallons a minute. So we can use our system sizer. We can use an electronic version of that if we want to start looking at line sizes. So if I run 3 gallons a minute through 3/4 inch copper, I get a pressure drop of about 2.8 feet per 100, or a velocity of about 2 feet per second. Whenever we're doing domestic recirc, keep a close eye on velocity. We don't want to move it too quick. I'll get to that in just a minute. If we choose a 1/2-inch copper pipe for our recirc line, again, from the furthest fixture back to the mechanical room, it can still handle 3 gallons a minute. The pressure drop goes up as well as the velocity. So I have to be careful on this velocity number. And again, I can use an electronic system sizer to give that same condition. There's a number of tools you could use to figure out what line size you would choose or recommend based on a given flow rate. Okay, so that's all we're doing here. Now, why do I care about velocity? Well, guess what? A lot of domestic recirc is based on copper pipe. And if you move water too fast through copper, you can erode it from the inside out, specifically around 90s, which is where you see very high velocities. Okay, as water is making a turn, it's pretty turbulent there, so velocity can be damaging to the copper because it's soft material. So most people are going to, if your water is less than 140 degrees, you're going to be looking at a max velocity of 4 to 5 feet per second, so you don't erode your copper from the inside out. For me personally, I'm always looking at 4 feet per second or less. I just want to be safe. If you're starting to see pinhole leaks in your system, pretty good indication that you've got too high a flow going through it. Okay. If you're doing really hot water, like to a kitchen or a laundry that needs 160, 180, yeah, you want to slow that down even more because you've got air in that water. It's hyper aggressive. Okay, so watch your velocity, and if you're having pinhole leaks in a system, good indication you're moving too much flow through it. Okay, so 3 gallons a minute is kind of our pump selection, and depending on that line length, if we assume 100 feet, we might only have 3 feet ahead. So in general, we could pick a very small pump for 500 feet of line because we don't need a lot of flow in our recirc system. We just need to overcome the heat loss. We could either use a standard little wet rotor circ, or we could get into a smart pump, kind of an ECM control if we wanted to. This would allow you to control based on return temperature. So the pump would speed up or slow down based on that 10-degree delta T we're trying to maintain. You could also do the same thing based on pressure. So if pressure increases in the system, we can slow the pump down. Depends how we're going to balance things. But either way, we get a very small pump for what we call our domestic recirc. The other thing we have to keep in mind is how are we going to balance our various floors? If it's a single-story residence, that's pretty straightforward, okay? But if you're a 3-story hotel or apartment building, water takes the path of least resistance. So water is going to tend to flow all through floor number 1 and right back to your water heater. Okay, if you're on floors 2 or 3, you might have some delays in getting hot water. So how do we get our recirc up to floors 2 and 3? Well, we start to choke down a balance valve. Okay, as we do that, we make it harder for water to flow through floor 1 and easier for water to head up into floor number 2. Now remember, we're not trying to boost it. We're not trying to lift water. It's a closed system at this point. The pipe is already full of water. City has taken care of that. All we're trying to do is circulate it. Obviously, I've left out a check valve here, kind of critical, but that's what we're talking about as far as flow balancing goes. How do you balance your floors? Well, you got some options as far as maintaining balance here. Now let's see, I've got another poll for you, so let me launch that real quick while I fumble my way through balancing. So let's talk about some options for you on the balancing side of the equation. One option is what we call a circuit setter, kind of a calibrated ball valve. It's a manually adjusted valve. Works very well for a constant speed pump. It just takes them back and forth to make sure that all your floors are getting the same flow. Okay. You could also look at some type of automatic flow control device. These tend to be ordered with a fixed orifice. So you could select each floor for half or 1 gallon a minute, whatever you'd like to see on that particular floor. And it's a spring-loaded cartridge that fluctuates with pressure to maintain a set flow. Okay, you're going to have a higher pressure drop across this valve, but they kind of self-balance once they're installed. You could some manufacturers also offer you a copper autoflow. So basically, it's a piece of copper, and if you open it up, there's an autoflow cartridge inside of it. We're not worried about low lead concerns since it's all a copper material. Very easy to sweat in line, and you're off and rolling. If you're looking for kind of a smarter option, B&G does make something called a temp setter. It's a wax-filled element that will allow water to flow or not flow based on return temperatures. So it kind of modulates itself. It's a smart valve. It always has a minimum flow going through it, but if your riser cools down, it's going to open up and allow more flow from your Recirc pump. As we get close to set point, it's going to slow itself down or modulate itself close to closed. This plays very well with an ECM or a smart pump where you could stage that based on pressure and let your pump speed up or slow down as this valve opens or closes. Okay, all different options as far as flow balancing. Okay, let me end the poll real quick. Thank you everybody for participating. If I had a poll about puppies and animals, might be more fun, but let me share results and we'll go through this real quick. What signs or problems may occur if the domestic hot water recirc is undersized, meaning too small? Please select all that apply. So thank you everybody for participating in this. Let's take a look. Temperature fluctuations will be seen at the shower. You might think so. I don't know that you're going to see fluctuations at the shower as much as this might be an indication that your master mixing valve is having some issues. Maybe, or for that matter, your water heater. But if you're getting hot water to a shower, but it's not consistent, that would indicate that city water is taking over and we're having problems leaving our water heater or with the master mixing valve prior to sending it out to the system. So probably not a recirc issue. Pressure fluctuations will be seen at the shower. You might think so. To me, that's more a sign of a pressure booster, which we're going to get to in just a few minutes here. But if your pressure booster isn't set quite right, or the hydro tank is giving you issues, that might lead to pressure issues at the shower. Long wait for hot water in the shower. Absolutely. If we got a big slug of cold water in this riser, and we have to wait for that to leave the system before we have hot water behind it, yeah, that's a good sign your recirc isn't working right. Frequent service required for the master mixing valve. This is another problem in the fact that if we don't have enough flow across our master mixing valve, it's going to tend to hunt, and that can lead to service issues. Okay. Pinhole leaks in the copper return line. This is a valid concern, but it wouldn't be the sign of an undersized pump. It would be the sign of an oversized pump or a pump that's running too much water. Okay, it just needs to be balanced back or undersized. Unable to get the conditioner out of your hair. Yeah, thank you. Glad somebody bought into that. That's not a problem for me. That might be more of a problem for Sunday, somebody with a full head of hair. A lot of that has to do with your water quality. If you're into hard water, that can cause that problem. You never feel like you're really clean, but not a sign of a recirc issue. Thank you, everybody.
Not a fan of that answer.
All right, so let's see how we're doing Sunday. We're running a little behind, so I'll keep cruising here. And Sunday, I'll get to questions in just a minute. Real quick, if we only need 3 gallons a minute, but we have an opportunity to put a larger pump in, we might fall for that and say, hey, yeah, if 3 gallons a minute is good, let's move 10 gallons a minute through that recirc. Be careful with that. More flow, lower delta T. Lower delta T coming back from our system is going to cause our master mixing valve some major problems. Okay, there's no source for cold water. The other problem we're going to have is really high velocities in that return line unless we've oversized that line for our 10 gallons a minute. So just be careful with oversizing a recirc pump. Okay, I'm going to talk real quick about a master mixing valve, and then we're going to end our section on recirc. So if you have any questions, now's a good time to start posing them. With a master mixing valve, one of the things you'll see when you select a certain valve size, we tend to pick them for a 5-pound pressure drop based on a set flow rate. Okay, so whatever our design flow is through that 2-inch riser, we're going to pick a master mixing valve to match that. The thing to be careful about, a master mixing valve might require a minimum recirc flow. So even though we've calculated 3 gallons a minute, master mixing valve might require 5 gallons a minute. Is this a problem? As long as we account for that line size, if we size our recirc line for 5 gallons a minute, not 3, we should be just fine. Okay, but there's a number of factors in sizing that recirc. One of them might be what's the minimum flow required by our master mixing, regardless of what's happening in the system. It's just a matter of balancing that out. Okay, and all a master mixing valve is doing is taking some hot water that leaves our water heater, and it's blending it with cold water coming from the city, or in our case, sometimes cold water coming back from our domestic recirc. That's why we need that 10-degree delta T to source a cold water when there's no load in our system. And that cold water mixes with the hot water to provide tempered water out to the system. So you might have 140 here leaving the storage tank. You might have 110 coming back from our recirc with the goal of providing 120 out to the system. Pretty simple, but it gets screwed up all the time. And a lot of it has to do with not only how we pipe the master mixing valve, but how we tie the recirc back into it. The recirc has to be able to flow not only through the water heater, but also to the master mixing valve. Okay, I'm going to fast forward through this, but we're just showing an open versus a closed system and the source of cold water going to that master mixing valve. Okay, forgive me, a bit of a crash course. If we can help with recirc issues, one thing I haven't touched on is various pressure zones, like a high rise, like the Bellagio shown behind us. Okay, there's different ways to approach that. But overall, a recirc is very simple. You just have to make sure you don't oversize it. And then when it comes to a master mixing valve, you have to make sure you tie them in together correctly. So we see a lot of issues in the field, people who overlook that or have some issues. Sunday, are there any questions before we move into pressure boosters?
There is one.
Okay, great.
We see a lot of engineers sizing the pump head per the building height instead of friction loss. Can you spend some time talking about the difference?
Oh, yeah, don't do that. Let me bounce back. Yeah, so just remember, this pressure drop through this recirc should really only be the line loss between the return line right here and the mechanical room. This pipe is already full of water. The city is taking care of that for you, or a pressure booster, depending on your system and how tall it is. Okay, but yeah, this recirc only has to overcome the friction loss between the mechanical room and the furthest fixture. So this is a friction loss. It has nothing to do with lift in the building. So yeah, if we can help on an example, glad to do it. If you want us to run the math on how we would come up with a recirc size based on your riser diagram, happy to do it. it'd be a lot to do here today, but yeah, if you want to shoot us something offline, boy, happy to get involved with that conversation for sure. Yeah, very good question.
Okay. Any other questions before we move on? Don't see any coming through, but you can always
Perfect.
add it towards the end of our Q&As, at the end of our Q&A session, or shoot us an email directly. So let's
Absolutely.
pressure boosters.
Yeah, we're moving into pressure boosters. Every time I think of boosting pressure, I think of the water show in front of the Bellagio. I know we might have some people on the call from Vegas, and lucky you, man. That's an awesome that's an awesome show. It's an awesome use of pressure. We're doing the same thing in a building typically, except we're not just shooting it up into the atmosphere. We're filling a pipe full of water, and we're adding some pressure behind it. Okay, so typically you've got city water that comes into your building, and it's going to fill that pipe full of water. But sometimes your building's too tall, and you don't have enough city pressure to get it all the way to the top of your building. Well, what do? You add something we call a pressure booster. Simply a pump or set of pumps that run in order to maintain a minimum pressure up in our penthouse or highest spot in our piping. Okay, that's all we're doing with the pressure booster. We're boosting pressure. Doesn't get much simpler than that. We make it look really nice. Okay, it's a fancy skid, control panels with a lot of buttons on it, lights, alarms, things like that. But you break it down, it's a pump that's spinning to generate some pressure in order to maintain minimum pressure up in the penthouse. We're simply we're boosting pressure. Now, something to keep in mind. All of these buildings might require 30 or 40 pounds at the penthouse, okay? But based on the height of the building, we're going to see a lot higher pressures in the basement of a high rise, a 70-story high rise, than we would a 30-story high rise. Okay, so our boost pressure or the pressure seen in the basement is going to vary dramatically based on obviously the height of the building. Okay, buildings, water has weight. If you're trying to maintain 30 pounds at the penthouse, a 30-story building, we might see 156 in the basement, or a 55-story building, we might see closer to 286 pounds in the basement. All that comes into what pump we're going to select, max rating on our header on our headers and components. Okay, all that needs to come into consideration. Now, one of the things we need to look at first is how do we figure out our flow rates? What flow do I need out of my pressure booster? Well, that tends to fall on something we call Hunter's curve. It's established in the 40s, a very conservative selection, if you will. But at this point, it's one of the few industry standards that we have to roll on. And typically, all you're doing is you're totaling up your fixture counts based on how many showers you have, whether they're private or public. Same with lavatories, laundry, kitchen. All those add up, and then you run into Hunter's curve. And based on the number of fixture units that you have, that equates to a given flow rate. Okay, and there's various scales for this, but they're all based on Hunter's curve. Typically for me, most engineers are giving me the flow rate. They're kind of responsible for that. Occasionally though, you'll get somebody who just wants to give you the fixture units and is relying on you to come up with flows. Hunter's curve tends to get you there. Now, once you have flows, you have to figure out, okay, well, how many pumps am I going to use if I need a pressure booster system? Well, you could use just one pump. That's cool until there's a mechanical issue with it. And then all of a sudden the building's out of water pressure, which isn't great. Most people on the commercial aspect are looking at least two pumps. So if one fails, they still have another to kind of back it up. You could also look at a 3-pump or sometimes a 4-pump system. One thing I should throw out real quick, a lot of these used to be constant speed. And as a result, we would see what we might call a jockey pump scenario, where you had a very small pump as kind of the lead pump, small horsepower, but it ran all the time. And if loads exceeded what that small pump could do, you would bring on a larger lag pump or backup pump, okay? Now that we're going to variable speed for most of our pressure boosters, we tend to see equal splits. so we can equally rotate our pumps through and the horsepowers are consistent. But you might see that more in the field. If you see a very small pump, it's probably set up as a constant speed with a jockey. Okay. You've got a lot of options. Whether you do there's a lot of different configurations for you. I don't need to get into this real heavy, but you can go horizontal or vertical with your pumps based on floor space. You can go to a triplex system if you like. And if you want to go crazy or you have a very big load, you can go to a quadplex or a 4-pump system. If you're a data center, sometimes they want multiple control panels, fully redundant systems. Okay, in this case, we had a flow here of 1,000 gallons a minute. Okay, that kind of dictates a lot of pumps. So rules of thumb, I might clarify this. Paul's rules of thumb. Okay, if your total system load is 50 gallons a minute or less, you might want to consider just a single pump with the second on the shelf as a standby. It might not be that critical, but it really depends on your application. Looking at a 2-pump setup, a duplex, if you will, anywhere around 250, 300 gallons a minute might be a good place, or less, might be a good place to consider a duplex configuration. When your flows exceed 300 gallons a minute, a lot of times you can save a horsepower by adding a 3rd pump. Also add some additional redundancy to your system. Okay, and then if you've got very large flows in a system, 600 gallons a minute or greater, sometimes a 4-pump system makes sense. But they're all going to stage equivalently. It just takes a little bit more floor space to add an additional pump. We're going to get to hydro tanks in just a few minutes, but that's the other thing to consider is what size tank might you need with various systems. Do you need one at all? We're going to talk about that in just a few minutes. But duplex, if you're 250 to 300 gallons a minute or less, we tend to default to a 300 liter or an 80-gallon hydrodynamic tank, well tank. And if you're greater than that in flow, we'll tend to go to a larger tank, 500 liter or 132 gallons. Why those magic numbers? 2 reasons. We stock them. And it's also kind of a price point that the industry will bear as far as an adder to a pressure booster. It doesn't break the budget, but there's definitely an advantage to adding a tank. We'll talk about that. Let's look at a typical system for a pressure booster. We tend to have some pressure losses that we need to account for. One of them is the height of the building. We talked about that already, and that's important for a booster, but it's not for a recirc. Okay. The other thing we need to look at is line loss, friction loss in here. But on the suction side, prior to the pump itself or the booster, we usually have a water meter and a backflow device that also eat up some pressures. We normally have city pressure at the street and then water meter and backflow that are also taking away from that pressure. So we have to account for all that when we're properly sizing our pressure booster. Now, a quick example. I gotta keep an eye on time here. Let's say we have a 13-story building that's 156 feet tall. Usually we assume 12 feet per story. Okay, if I can do some quick math, I can figure out that I need about 68 pounds in the basement to get water to the very top of the building. What's not accounted for here is that water at the top is going to be at 0 pounds of pressure. If I've got somebody who needs a shower up there, they might need more than that. So typically we design for 30 or 40 pounds minimum at the very top of the system. Getting water to the top, I might have some friction loss in that riser that serves the building. So I need to account for that. If I'm using a hydro tank, I need a pressure band for that tank to work on. So we need to account for that as well. And then my pressure booster might have its own losses, like a check valve, losses through some headers, and or isolation valves. All of that comes into play. So if I had 68 pounds in the basement, I'm not really going to serve this building too well. If I have 128 pounds in the basement, now I can do something. Somebody can take a shower up here with 30 or 40 pounds of water and be comfortable in their nice penthouse. Okay, back to our little riser schematic. My booster is controlling to 128 pounds of discharge pressure in order to maintain a minimum of 40 up here in our penthouse. That's all that's happening. Very simple. Now we have a worksheet that we tend to send out to a lot of engineers because we get tired of asking the same questions over and over again. No offense to anyone on this call, but the first thing we need to size a booster is what's our flow, okay? And normally that's specific to each building. We also need to know what kind of pressure we have available to us at the street, or we take a guess. Typically it's anywhere from 40 to 60 pounds, at least in Portland. And then we need to account for our water meter and our backflow, okay? And those do have a substantial pressure drop we have to account for. So if you think about this, coming into our building at our pump location, we might have 44 pounds of pressure available from the city. We know based on our building height and minimum pressure in our system, we need 128 pounds of pressure in our basement. Well, 128 minus 44 gives us a boost pressure of 84 pounds. Once I know that magic, now I can go select a booster, okay? Now the difference would be if you're pulling out of a break tank or a day tank, these numbers go to 0, okay? But if you have access to city water, that's an advantage for you. So again, if I'm trying to select a booster for 150 gallons a minute at about 84 pounds of pressure, I can just roll over where those lines intersect and select a booster. Most manufacturers have selection charts. We have our own in-house that we're happy to share, but it makes it very easy to select a booster. Overall, this process takes about 10 minutes. Once we know the height of the building, the flow, we can make some educated guesses to dial in a booster. We also have some selection software online that does that same information for you. We'll give you a header size, a 3-inch, check valve sizes, operating weights, full load amps, and overall a submittal package that you could download, okay? It's all based on your criteria for discharge pressure and city pressure available. Okay, we're doing all right. One of the main components, and forgive this slide because I know it's not really interactive, but I just wanted to touch on the brains of this system that we call a control panel. It's doing a lot of monitoring for us, but operation-wise, it's very simple. It is controlling pump speed based on leaving pressures. So if we're targeting 128 pounds in our system, it's going to speed up or slow down our pumps to maintain that 128 pounds, okay? Tends to monitor this every 2 seconds, every 2 to 6 seconds. So as pressures fluctuate, as loads change in our system, it's telling the pumps, hey, I need more pressure or I need less pressure, and they speed up or slow down. It's really that simple. There is minimum run times for the pumps, and if we satisfy that minimum run time, and the booster thinks it's okay to shut down because it's been at the same speed for a while, one thing the control panel will do is it'll bump system pressure. It'll raise it by about 5 pounds. And it comes over here and it checks, hey, does that pressure stay high? If so, it means nobody in the building is using water, and it's okay to shut the pumps down. If that pressure drops, somebody's still using water, and the pumps continue to run. Okay, it's all part of a sequence. Controls are very advanced. Pumps are very simple. Generate pressure. An old school panel, forgive me, this isn't what we're seeing a lot of today, but if you looked inside this might give you a better feel for what's happening inside a typical control panel. Kind of a main disconnect for all power, so you could service this. Also individual disconnects for each drive, which are tied to each pump. So if you had to take a pump out of commission, you could do that here. Controller, transformer, and the thing that's unique here are cooling fans. Okay, so if you have drives inside a panel, they give off heat, so you need to cool them down with room air. If anybody's looking for a spare toilet paper, got you covered. Okay. Obviously, pre-COVID, you might see boosters that are a little smarter these days, where they're using ECM motors and drives that are mounted on the motor themselves. Much smaller control panel, with a touchscreen control interface that's telling the drives and or motors what to do, speed up or slow down. Okay, a lot more compact footprint. Touchscreen controls that allow you to set your pressures, your minimum run speeds for your drives to maintain that system pressure. Also, there's a lot of alarms that the control panel is watching for. Max pressure, minimum pressure, a lot of things that it is tracking. Okay, I've got a poll for you. Let's see where we're going. Hydropneumatic tanks. Bear with me a second here. Let's launch our second to last poll. Keep an eye on time. Okay, I'm going to fast talk through you, if you will, on hydropneumatic tanks. Why do we use them? Where do you put them? How do you size them? Okay, let's talk about an old school system. What did we do in the old days? We had a city water line that came into the basement of this building. We had a pump that simply transferred that water up to the top into a gravity storage tank. Open atmosphere. It was working on a float valve. So as that float valve satisfied, the pump in the basement would shut off. Okay? As people used water in the building, the float dropped, the pump would come on and reestablish that water level. Seismically, a bit of a disaster. Okay, if this building starts shaking, you don't want to be down here on the sidewalk. Also, if you paid a lot of money to have a penthouse with a nice view, you didn't have a lot of water pressure up here. Your only water pressure was limited to the height of the tank relative to tying into the building. So these days, we're getting away from those gravity tanks. Surprisingly, you still see a lot of them in New York City, but new design, what are we doing? We're capping this right here, and we're adding additional pressure to it in the basement with some type of variable speed pressure booster. Okay, so the guys in the penthouse will have their 30 or 40 pounds of pressure without having to elevate this tank really tall. Let's assume that this that we're going to cap our riser and that we've got a minimum pressure in our penthouse of 30 pounds. This works just like an expansion tank. It's a little bit different, but very similar. If our minimum pressure in the penthouse is 30 pounds, we're going to want 30 pounds of air set up into this tank. Okay, so those pressures match. Now guess what? When we get to 29, we start our pressure booster. We start to build pressure. Remember that 10 pounds that we added into our sizing? That extra 10 pounds goes to add more water to this hydropneumatic tank. Okay, when we add more water to it, guess what? Our air compresses and gets higher in pressure. Now our pump satisfies, shuts down, our pressure booster is no longer running. But in the penthouse, we now have 40 pounds of water pressure because we've got 40 pounds of air behind it. When somebody goes to open a faucet or take a shower, we've got 40 pounds of air that's pushing that water back out into the system. Okay, so this water heads out into the system to meet the load, and when it gives up its volume and drops to 29 pounds, we start the pressure booster again. That's what's happening with the hydropneumatic tank. It's storing water and then giving it back to the system while the booster's not running. A couple real important things. Most hydro tanks have 1.5-inch, 2-inch, sometimes 3-inch connections. You want to make sure you run that full line size into the riser. You don't want to neck this down from 2-inch down to 3/4 and run a 3/4 line into the system. You can't get a lot of water out of that tank with 3/4-inch line, okay? So you want to run full size from the tank into your riser connection. Where do we put this tank? And forgive me, I got a poll, so I got to figure out what I should do with that. Let me end my poll and we'll share results, and then I'll open a class survey while we wrap this up. So bear with me a second. Forgive me for not being more on track here this morning. What are true statements relative to hydropneumatic or well tanks? Are not required for a pressure booster system. That's true. They are not required. Only add value when the air charge is set correctly. Again, true statement. If the air charge isn't right, all bets are off. You might as well isolate that tank. Help to buffer system pressure spikes from flush valves. 100%, yes. There's a lot of pressure fluctuations that happen in our system, and that hydro tank helps with that. Causes the booster run continuously, wasting energy. Yeah, that's not right. Are heavy and should be installed in the basement. We'll talk about that in just a second. You would think so. I don't think they're as heavy as we think. Overall, what's a hydro tank do? It allows your booster to shut down. It allows it to not run, and it stores water until somebody needs it. Is it required for a pressure booster system? No, it's not. Okay. Is it a cheap insurance? Is it potential energy savings? Absolutely. Thank you for participating in the poll. Now, I should launch my last one while I work through where do we put these tanks. If you decide to use one, okay, where do you put it? Do you put it in the basement or do you put it at the top of the system? Now, I hope you appreciate the play on this picture. Okay, this is our tank. Question is, where do we put it? Do we put it in the basement or do we put it in the penthouse? Let's assume some pressure's in the basement, and I'm just making up random numbers here. Okay, let's assume that I need 85 pounds as a minimum, and with my booster running, I'm going to target 95, so that's at my 10-pound band. Hydro tanks run off of something we call a drawdown factor, and that's working on the pressure band in our system. So if our minimum's 85 and our maximum's 95, that gives us a drawdown factor of 0.091. What does that mean? That means if you've got a 100-gallon tank, we'll get 9.1 gallons of usable water back to the system when our pressure starts at 95 and drops to 85 before we start our pressure booster. Okay, so a 100-gallon tank only gives you 9 gallons of usable. That's a little disappointing. If we take our tank and we elevate it, okay, and we take our tank to the top of our system now instead of the basement, well, we're running lower pressures up there. We're going to have a minimum of 30 and a max of 40. What does that do for us? Well, we go to our drawdown chart. If we have a minimum of 30 and a max of 40, well, you'll see our drawdown actually improves. It goes to 0.183. So that 100-gallon tank gives us 18 gallons of usable water. So we actually get more water by having our tank in a lower pressure zone. That's a good thing. Okay, now if you're a corporate trainer for CHC and they have a tank they're going to take to the dump because there's a scratch across the ASME nameplate, but at home you're on a well system, and you could use a big ass hydrodynamic tank. Okay, that's what this is. You come to a draw, and you got 3 teenagers at home. You come down to a drawdown chart and you figure out, okay, where do I want to set things? Commercially, we tend to run on a 10-pound band, so nobody complains about spiking pressures. Notice if I run from 30 to 40, I got a 0.183 drawdown factor. Residentially, you can most guys will work on a 20-pound band, okay, which again extends that drawdown. At home, I run on a 40-pound band. Why is that? Because my wife and kids don't complain, and it allows me a 0.472 drawdown factor. Well, what does that mean? That means that my 528-gallon hydrodynamic tank stores 250 gallons of usable. And when my pump runs, it runs for 21 minutes, and then it's off for 2 days. So I don't short cycle my equipment, and I've got the advantage of having a really large volume of water stored. So when the power goes out, I don't have to worry about running to the store to pick up water. Now, let's talk about where do you put tanks. Do you put them remote or do you put them in the basement? Well, you might call this Paul's rules of thumb again, okay? But if you've got a building that's less than 12 stories, it might be just as simple to put the tank right next to the booster in the basement, okay? Hydrodynamic tanks are good to 125 pounds of max working pressure. So as long as we don't exceed that, it makes it easy on the install, it makes it easy on the startup to have everything in the same mechanical room. Are there advantages to putting the tank remote? Absolutely. And if you've got an easy spot for it, perfect. But is it worth fighting an architect or a mechanical to eke out a little bit of space Maybe not. That's your call. Okay. If you've got an elevated building, something that's greater than 12 stories, yeah, this is the time to have that conversation. You get more drawdown out of the tank. You don't have to pay for a high pressure hydromatic tank, because if you put it remote, it's running in a low pressure zone. So now you can use a standard tank and just put it remote or elevated. And by the way, it doesn't have to be at the very top of the building. It can be in a stairwell. It could be in a janitor's closet. We've seen a lot of interesting installs. Anywhere that's close to the main riser where you can just tie it in, that works. That works perfect. Okay, how do we do? Sunday, we've got 7 minutes left. 6 maybe. If there's any questions, now's a great time. I hope that helped everybody on a Recirc and pressure booster. We just want to give you kind of a quick overview. And boy, there's a lot of things we can help with. So if you've got specifics, shoot us an email. We're happy to jump on that.
We've got a few questions.
Oh no.
Are you ready? Here we go. Is there an issue with high pressure in the pipe at the bottom of high-rise systems?
Yeah, good question. It really depends on the pipe you're using, and I can't speak of that too much. Whether you're doing a grooved or Victaulic style pipe versus a welded, yeah, they're all going to have different pressure ratings. Something to keep in mind, but I'm no expert there. So yes, you have to be cognizant of that when you're laying out your pipe system. Obviously, water has weight, and the taller your building is, the more weight you're going to see in the basement, unless you separate it out with some type of heat exchanger or various pressure zones. There's different ways to account for that. But yeah, those all come into design considerations. Good question. I don't have a solid answer for you, though.
Where there's a couple of pressure sensor questions.
Yeah.
First one, where is the best spot to put the pressure sensor? At the top of the riser or at the pump?
Oh, yeah, really good question. So we have tried remote pressure sensors. So let me go to a standard riser. Let me go back to this guy. Bear with me a second. We've tried remote pressure sensors. So this one on the discharge header headed out into the system, it's part of the pressure booster package. So it's installed by the manufacturer. It's wired to the control panel. Excuse me, there's nothing to do in the field. So that's an advantage to having it right here at the booster. If you take this, another option or thought is to take this pressure sensor and run it to the very top of our building. I don't have an easy schematic for that, but run it up to the 12th or 20th floor, wherever you want to install it. You can do that, and we've tried it. The challenge is nobody wants to be responsible for that wiring because it's low voltage. So the control contractor doesn't want to do it. The mechanical surely doesn't. And electrical tends not to want to touch it either. So that's your first challenge. The other challenge is if that remote pressure sensor gets isolated from the rest of the system, then your pumps can run out of control because they're not seeing the true system pressure that's occurring in your riser. So we find that having it on the header is a much safer location. Controls are smart enough to be able to offset your pressure depending on how many pumps are running. So if we're assuming a friction loss in our riser of 10 pounds per se, as we get 2 pumps running, instead of targeting maybe 100 pounds in the basement, we can target 110 to offset the friction loss that we're going to see in the riser. So controls can help us with kind of faking out a remote pressure sensor. So that's really the advantage of installing it remote, is you're monitoring it accurately, but software can also kind of help with that situation. Really good question, and can certainly get into more detail if you like.
Second question, which you may have kind of covered in that first response, but also on pressure sensor. Should the pressure sensor controlling the booster ever be located out in the system by the hydro tank, or does it operate fine near the booster discharge head?
Yeah, but same point. It does operate, from my perspective, it operates better right near the booster. and we can tweak software a little bit, or our program, to offset that pressure if you're concerned about the friction loss in the riser between basically the pressure booster in the basement and your furthest fixture or your penthouse. So we might have some line loss in this riser. And if you want to maintain an accurate pressure near the penthouse as loads fluctuate, obviously as we send more flow through this riser, we're going to see more friction loss. So we can offset that with our set point. Software is smart enough to do that based on how many pumps are running. But yes, much simpler to have it factory pre-installed right here at the discharge sensor than trying to do it remote in the field. It causes a lot of headaches. That'd be my take.
Great.
Hope that helps.
Yeah. Carl said you can put the tank in his driveway. So that's.
Yeah. By the way, it looks like a small bomb going down the road, depending on what you're hauling it with. I got a lot of interesting looks headed there. But yeah, you're going to need a tractor or something to offload that sucker for sure. And
then Hans has a question / addition.
Yeah, sure.
HP tank not required, ? True, the system will work, but the pressure will be all over the place and the pump will cycle on and off when water fixture is open. The building owner won't like this result and the pump will require much more maintenance.
Yeah, a real valid point. So Hans, yeah, to your point, high pressure tends not to be required if you can put your tank remote or elevated in a lower pressure zone, which I think is what you're referencing. Every booster startup that I've been involved with where there is not a hydrodynamic tank, the first thing the contractor asks is, so why isn't the pump shutting off? Well, anytime there's a load in the system, pressures fluctuate slightly, and that's enough to keep that pump running. So again, if you want the pump to shut off and save you some energy, you need somewhere to store some water. So at an elevated pressure, so when there is a slight load or even a leak in your system, that water can give itself back before we start the pump again. All manufacturers have very advanced control platforms, so it's not based on the control panel. It's based on whether you want your pumps to ever shut down or not. If to Hans' point, you're also, as flush valves, pressures can fluctuate dramatically in a system, and that hydrodynamic tank helps to buffer that out by having some volume there. But yeah, all valid points.
Hans, I unmuted you, so.
Okay. Yeah, I was just mostly, and I agree with everything you say, Paul. I was just mostly referring to when you were, going over the poll questions, there was like, yeah, tank isn't needed, for a booster system. And keep in mind, there is a specific manufacturer out there who is saying you don't need one, but because of the sophisticated controls, because we ramp up in the acceleration and the deceleration rate of the VFDs purposefully, no variable volume system can keep up with a flush valve. So yeah,
you're right, Hans. And my point there too is manufacturers who claim they don't need a hydrodynamic tank are just trying to get a price advantage because they expect all other booster manufacturers to provide a tank. If you're going to emit a tank, emit it for everybody, because ultimately controls are advanced across the board. And if you decide you don't need a tank, that's fine. But from our experience, there's a big advantage to having it in the system. It does stabilize your pressures, and it's not a huge cost impact either.
Right. Yeah. Good point. If you're gonna omit the tank, use somebody else's booster. Thank you very much, Paul.
Yeah. Thank you, Hans. Good point. And guys, listen. I hope this helps everybody. We're just I see it's too basic for some. Others learn something today. We always appreciate when you learn something, whether it's just one component. But yeah, we appreciate you attending today.
Yeah, we have one more quick question. Well, it might not be quick, but we have another question. What is the best way to figure out how many stages you would need inside the booster pump to give you the best results for what you need?
How many stages? So yeah, it's an interesting question. I'm not sure if we're talking stages on the pump or stages as far as how many pumps to utilize based on flow rate. Typically, we have our own rules of thumb for that, but a lot of it, for me, is looking at horsepower requirements as well as available footprint. There's advantages to sometimes a duplex and price point. So a duplex is going to cost less in general than a triplex, a 2-pump versus a 3-pump system. But sometimes your electrical use is going to be lower with a 3-horse, because majority of the time a single pump is going to be in operation. It's rare that you're going to see full load in a system, unless it's initial startup or there's a big power outage and you have to refill all the risers. So all those kind of come into play or factor. We can certainly help with that evaluation, but it's a tough one to decide without a price book in front of you, without looking at horsepower curves specific for each pump or model number, and then obviously footprint. Yeah, it's a really good question. To me, it's one of your evaluations as far as looking at your mechanical room space, how much redundancy you'd like to see in the system, and ultimately what the budget is.
Okay.
I hope that helps.
Looks like that was the last one. All right, everyone, thanks for hanging in there. We appreciate your time and so glad you could make it today. As always, if you have any further questions on this topic, you could reach us via email. In addition, we have another session of this same class on Thursday. If you feel like you need to go through it one more time, feel free to register for that. That one's at 2 p.m. on Thursday. Otherwise, the recording will go out sometime early next week of this class to all of you that attended. Thanks so much, and we look forward to seeing you in the next class.
All right. Thank you, Sunday.
Thanks.